Okay, so this lesson is on transformers. Basically, they're not robots, but they're essentially an iron core shaped like this, okay, with coils of wire on either side. So, what do I mean by that? If I have a voltage supply on this side, okay, let's say this is the positive end of the battery, rotate it around like that, okay, goes to the negative end of the battery. So what's happening here? Current is going to pass through from the positive end to the negative end, okay? Now, in a previous video I told you that when we've got current flowing in this direction, shown by the thumb, this is the this is just the screwdriver rule, okay, right hand screwdriver rule. If current is flowing in that direction, we've got a magnetic field going around it like this, okay? So that means as current is going around this iron core, a magnetic field is also present in this around the wire, okay? And more importantly, if we've got an AC supply, okay, let's say this is no longer a battery, okay, but I change this to an AC supply, okay, that means current is going back and forth, okay, along this wire, okay, at a certain frequency. That means we've got an alternating magnetic field going back and forth as well, and a magnetic field has got a range, okay? Now, this side of the iron core isn't that far from this side, and it will also experience that alternating magnetic field. If I now just do one coil of wire on this end, I am going to actually get less current or less voltage flowing through this end, this wire compared to this. And this is what we call a step down transformer. Why is it a step down transformer? Is because the voltage on this side is going to be greater than the voltage on this side, and it's given by this equation. V2, which is the voltage on this side, the secondary core, over V1, the voltage in the primary core, is equal to the number of turns in the secondary core divided by the number of turns in the primary core, which is the first core on this side. Okay? And if I give you some values now, you can do a calculation. So let's say we've got 10 turns here, and we've got 1 turn here, and the input voltage is 230 volts, and I want to work out what V2, the final voltage. So V2, if we rearrange this equation, is going to be N2 over N1 times V1, which is the input voltage, and N2, that's the number of turns in the secondary core, that's 1 over 10, because N1 is the primary core, times 230, okay, that's a tenth, times 230 volts, that's 23 volts, okay? So that means we've got 23 volts being produced here, okay? So that's why it's called a step-down transformer. So let's say this could be your laptop or whatever electrical device that requires 23 volts. So 230 volts will come from the socket, okay? However, inside your laptop plug, okay, it's what we call an adapter, there will be a step-down transformer to reduce the voltage, and it uses this principle, okay? Right, where would we use a step-up transformer? We would use a step-up transformer from a power station going into the national grid or the pylons around the country. Okay, so pylons are these things that transfer electricity around the country. Okay, and let's say this is my power station. Right. So, let's say the power station produces a voltage of 25,000 volts. Okay, that's quite high. Now, believe it or not, in between the power station and the first pylon, we have a step-up transformer. So you might be saying to yourself, why do we have a step-up transformer? Well, a step-up transformer, as the name suggests, will increase the voltage. The reason why we're increasing the voltage is because the power lost is given by this equation. P equals I squared R. Okay? And that comes from this P equals I times V, but V equals IR. And if we substituted V, we would get P equals I squared R. Okay? Now, this is the energy lost as heat, as current passes through the wire. Okay? It's given by this equation. So what does this equation tell us? Well, the higher the I, okay, squared, for a given resistance in the wire, we're actually going to lose a lot of power, or energy per second. And that form of energy is going to be heat energy, okay? So, basically what's happening, the more times electrons are flowing through a bit of wire, so if I just say here are our atoms in the wire, okay, and we've got the electrons that are going to pass through. Now, if we have loads and loads of electrons passing through the atoms really, really quickly, they're going to bash into the atoms, friction is going to be caused, so we're going to get a lot of heat energy being produced. Okay? So actually, if you pass a lot of current through a wire, it actually glows, it heats up. So heat energy is lost in high current. So, why is this important? Well, according to the equation, P equals power equals current times voltage. If we increase the voltage, okay, from a step-up transformer, we're not actually losing power, but the current is going to be reduced. Okay, my power is still going to be the same. Okay, not much power is lost. But current is going to be actually quite small. So these pylons will actually have a huge voltage. So say 300,000 volts. Okay, that's much larger than our 25,000 volts. Okay, produced at the power station. So what is a step-up transformer? Right. Well, again, same principle. Got a hole in the middle made of iron. Why is it iron? Because iron is a good magnet. Okay, it can be magnetized. So, step-up transformer will have less coils at the start and more coils at the end. Okay? So, let's just calculate this. So, we start off with 25,000. So, input voltage is going to be 25,000 volts. Output voltage is 300,000 volts. Let's say I start off with 10 turns and I want to work out how many turns in the secondary core. So I write down my equation, V2 over V1 is equal to N2 over N1. I want to work out what N2 is. So N2 is V2 over V1 times N1. That's 300,000 over 25,000 times 10. Okay, so do that on your calculator. Okay, you get 120. So the answer is 120 turns is required in that secondary core. Okay? So, that's the basic principle of transformers. So, let's do some questions just to verify your knowledge. So, a transformer has 20 turns on the primary core and 400 turns in the secondary core, what is the output voltage if the input voltage is 500 volts? Okay, so basically now we need to translate what we've done into being able to apply it to a question like this. Okay, so we've got no diagram, but we can list what we've got. So primary core voltage or turns is N1, that's 20. 400 on the secondary core, N2 is 400. Output voltage V2 is 500 V, and we want to work out what V1 is. So let's write down our equation. V1 equals N2 over N1. V1 will be V2 times N1 over N2. Okay, so let's put in the numbers. So equals V2 500 times 20 over 400. That is 25 volts. Okay. Right, explain in terms of magnetic fields how a transformer works. Right, so I've already actually done this, but I'll just write it out for you. So basically, an alternating current on one end of the iron core will produce an alternating magnetic field. This alternating magnetic field will induce, this is the key word, an alternating voltage and current in the secondary core. Okay? And then we can say, depending on the ratio of coils in the primary and secondary cores, we can cause the voltage to increase or decrease. Okay, so that's the sort of answer you would like to have in order to answer this question. Okay, and just finally, we just want to extend this equation. We know that V2 over V1 equals N2 over N1, but actually, did you know, because V is equal to I times R, I and V are proportional to each other, we can actually put I2 over I1 as well. So current in the second core, and this is current in the primary core. Okay, so if you get a question where it's telling you the current in the secondary core, the current in the primary core, you can use this relationship as well. Okay, so you can have I2 over I1 is equal to N2 over N1. Okay, and that's the end of the lesson.